So let's implement this numerical integration in Python and compare with an analytical result. Let's see how this works. So the principle is again given here in the notebook, is we will replace the integral over a function f of x, in our case between -1 and 1, by basically replacing it by a polynomial and then integrating the polynomial. And this leads to, in fact, to simply multiplying the known function at the collocation points, the GLL points, with the weights that we get from tables and from a subroutine. Now let's see how this works. Well, first of all, let's initialize a x, the space coordinate, between -1 and 1. We use 1,000 points for this. And we initialize a function. I've given a function here, x plus x squared plus sine x, just to try it out. And in the further course material, you're encouraged to actually change that and try very different functions. For example, a sum over sine or cosine functions. Now, in this case, the analytical solution of the integral is actually 2/3, so very, very easy. Now, we start with an order 2. So we can now, and also in terms of understanding what happens here, we calculate the function approximation of f using Lagrange interpolation, and compare it with the original function, and then look at the result of the integral. We've already learned how to calculate the interpolated function using Lagrange polynomials, so I'm not going to focus on this. Now, the core of the scheme is, of course, very simple. The numerical solution of the integral is simply here calculated in this loop. We just multiply the function values fi at the collocation points I with the appropriate weight here, w, and that produces the numerical solution of the integral. So now let's see how this works. Here's the solution to the problem. Now we have space between -1 and 1, and our analytical function is actually the black line here, and we've interpolated with order 2 polynomials. So we have these two intervals, or 3 collocation points that are given and seen in these blue squares here. So there is a slight difference between the polynomial, but the value of the integral is actually already very well represented here, but that's actually due to the specific function that we've chosen here, which maybe might not have been the right choice, but you can change now this to any function and see whether your analytical integral is well represented or estimated by the numerical integration procedure. So let's change here the order. Let's go up to, let's just take an order 6 here, for example, and run this again. And now you can see that the Lagrange interpolation works extremely well, and we're fitting the analytical function very well. Of course, that also implies that now the value of the integral is well represented. So again, please play around with this and appreciate this numerical integration scheme. This is actually the part of the spectral element method where the error in the space comes from, because it doesn't come from the interpolation. Interpolation is correct. It's this numerical integration that leads to a small error that, of course, contributes to the overall error of the solution.